Resume record. Yep, thank you. So as you can see, image binarization is a process of converting any image into a binary image, so meaning 0 and 1s. And it's very useful in the case where we want to do something like segmentation or like segmentation-like. So we have a white cat in this case and on a blackish background. So most of the pixels of the cat are going to be close to 255. Most of the pixels of the background are going to be close to 50. If we put something or a threshold of 100, we're easily going to set all of these to 0 and the pixels of the cat to 1. So this will give us the mask or the segmentation of the cat. Say it was the opposite. So basically now instead of having a white cat, we have a black cat, for example, on the snow. This means that the cat's pixels are very close to 50, whereas the background is very close to 265. And again, you can clearly make a separation. So you can see that this algorithm works very well when there is like a big difference between the foreground and the background. But in cases where they are very similar to each other, this will not work. So there are many segmentation methods, many of them that are similar to this thresholding technique. Some of them are working with different thresholds. Some of them, they use different algorithms to find the perfect threshold. We will see the majority of them in this lecture. And then we will speak a bit about image gradients and how can we, instead of using thresholding, how can we use edge detection to basically find the object that we're looking for and segment it. And here we can find different edge detection techniques. So there are gradient filters, like here. There is Laplacian of Gauss, which is a good one. And there is the Canny edge detector, which is kind of the best, but nobody uses it anymore, okay? So all of this is just history. So for the segmentation method, we're going to speak about thresholding. So thresholding is generally an operation that is generally used in order to separate some objects of interest from the background. So the object of interest is usually called foreground and the background is basically called the background. So in this case, for example, here we have the set of cards and we're trying to basically separate these cards from the background. You see that the main problem is the color of these pixels is very similar to these pixels. So if you wanted a model that will separate like this, you are kind of out of luck. But if you wanted just a simple model that can separate, for example, the 10, the G, these signals and stuff, which are quite useful, for example, for further processing, then in that case, you might find this interesting, right? You might find this thresholding operation very useful. Here, for example, in this image, it's very difficult for a machine learning model to understand that this is N, this is like X and V, but on the picture on the right, so this one is much more useful for machine learning models to learn from, right? So this is like, this could be the goal of using thresholding in this situation. So this is a simple operation or a simple manner to kind of speed up the segmentation method. I think this one will be explained in the labs a bit better. So let's skip it up for now and go to more complicated tasks. Here, we are going to see that thresholding is in fact not a very simple task. So for example, if you have in this case, if we have like, let's say this case is a threshold of 150. So you can see it's working well. If we chose a threshold of 100, it wouldn't work very well, right? So it's only taking the darkest pixels. For example, these pixels, which were not very dark, meaning they were closer to white or closer to 265, they were not taken. They were kind of forgotten. Let's say this one was 50, and in this case, no, this one is like 200, right? Let's say this is 200. And it's basically taking everything as a dark pixel. Meaning finding the best value for thresholding is not an easy task. And in some cases, Even the perfect value, as we have seen here, give a lot of problems. So there's no such thing as like the optimal or the best thresholding method. But I think the most logical technique is the following, right? So basically what we are going to do is we're going to represent the data in their, or represent the values of the pixels in this sort of histogram, where we have like the intensity of the pixel, or like the color of the pixel. And here we will have the number of pixels which share the same value, right? So in this case, we will have this kind of distribution, right? What we have noticed in like the easy tasks of a segmentation, we usually have very clear or two very clear distributions, or two very clear peaks in our distribution. This is why it's called a bimodal histogram, meaning it should have something similar to two Gaussian distributions. These Gaussian distributions might be like the same, they might have the same size, one might be bigger than the other. Depends on basically whether the foreground and the background are closer together. So can somebody tell me from now, what would be a good way of putting the threshold here, right? A small algorithm, very basic value that could be used as the algorithm for separating these two, background and foreground.
Maybe we could take an average color for the whole image and
Exactly, amazing answer.
based on
So let's say we take the average color, right? In a perfect scenario, this is a great example, right? So in a perfect scenario where we have like a cat here, the cat has like pixels which are mostly dark, and then we have like a background which is white. In this case, like if we assume that the size of the cat is like 50% of the image, the size of the background is 50% of the image, then taking the average would fix this problem directly, because it would be something close to like 125, right? And everything that is bigger should belong to the background. Anything smaller should belong to the foreground. So this is a perfect situation. But what if we have this problem, which is the most common problem ever? The cat is very small inside the picture. Meaning let's say we only have 10% of the pixels as black and 90% of the pixels as white. This means if we take the average, the value is going to be very high, like something around 225, for example, right? Because it's highly influenced on these white pixels. So the white pixels are the ones which are making most of the problems. So in this case, you have a threshold that will just split up different parts of the background, and the foreground model will be like splitted between different parts, like just random, right? So this means that the threshold that we taken as the average does not work in this situation, which is a very common situation. This is why they introduced something a bit more complicated than the average. So what they decided to do is basically calculate these, and then we take this point, right? So this is the point as the threshold, or the place between the two different peaks. So how do we build a histogram? Very simply, right? Let's do it kind of together. Let's say number 1. How many ones do we have? Just one. How many 2s do we have? 1, 2, 3. Sorry. How many 3s do we have? 1, 2, 3, 4. How many 4s do we have? So 1, 2, 3, 4, 5, 6. How many 5s do we have? We have 1, 2, 3, and 4. So this is how you build this histogram. 6, for example, we have 1, 2, just 2. How many 7s do we have? We have a lot. 1, 2, 3, 4, 5, 6, 7. How many 8s do we have? 1, 2, 3, 4, 5, 6. I think it's either 6 or 5. Huh? How many 9s do we have? 1, 2, 3, 4. So we have 4. And here we just come here and build a simple distribution. So let's say this was 1, then it goes up to 3, then it goes up to 4, then 5, 6. Sorry. So it should be 1, and then 3, then 4, 4 with 6, and then 5, then with 2, then goes back up to 7. Yep. Well, it should look something like this. So this is basically our histogram. And here we can clearly see that there are, again, 2 peaks. And this is like the value in between. Very well. So again, this was the histogram. These are the values that we found. The 2 peaks can be seen again. So yeah, can somebody tell me how, or can somebody give me an algorithm? Now that we have this bimodal histogram, how can we separate it? How can we find the threshold in this example?
Gradient descent, maybe.
What did you say?
Gradient descent.
Gradient descent. That's a very, very good proposition. But there is one problem with this one. It's the following. First, this is not a continuous function, right? So it's not something that you can derive. This is more of a, like this kind of function. Right? So we represent it in a line just for explanation, right? But in reality, it's not a continuous function. It's a very discrete function. And the second problem is, even if it was, you have all of these problems here. So like all of these local minimums. See?
Maybe we can use some different approaches for optimization, like simulated annealing.
Exactly. Yeah, go ahead. Give me some different approach for optimization.
I already said simulated annealing.
Simulated annealing. Okay. That could be nice if you have this. Actually, it's a very good proposal. Can you tell me what would be the fitness function? If I'm not mistaken, simulated annealing is about what is it called? I forgot the one. Yeah, where we represent a value in like this, and then we just crossbreeding and stuff like that. No.
I don't remember too, but I remember that it can deal with this form of function.
Okay, can somebody give me like good? Can somebody give me something that is easy, right? Like something very quick and easy that jumps to mind.
Why don't we take the minimum value between the 2 peaks?
Exactly, but you have to define the 2 peaks. I like this answer, but we have to define what are the 2 peaks.
We can get the peaks by regions.
By what?
By regions. If we know like some kind of range, we can get like, for example, the first, like if we say that this is the maximum value in like, let's say 100 points, like since our range is 250.
But who can set the range?
We can, like, I think we can set it manually, but I'm thinking of something automatic.
You see, so for example, if you have like a, I don't know,
if the 2 peaks are very close, that will not work.
Yeah, exactly. So if you have the peak 1 in here, peak 2 in here, they are all in the same region, right? So can somebody give me something else?
Could we use moving average? Oh, just filtering until we get 3 peaks and pick the second peak, like the minimum.
What do you mean a moving average and take the? What do
I
you
mean, just simple filtering by convolution with ones and yeah.
I see. Let's think about something closer to like bimodal histograms, right? So bimodal means that there are two distributions. We said that bimodal means that there are two, what are they called? Help me out. Two normal distribution or two Gaussian distributions. There is this one and there is this one. Do you know of an algorithm that can basically find the calculating the differences, maybe? Yeah, something definitely close to this area, right? So do you know of an algorithm that can basically find the mean or find the parameters of these two distributions from the data? So we're going to find something that is empirical, something that will take just two distributions or find the best two distributions that fit this data, right? Have you have studied KL divergence?
Yes, at least data scientist.
You have studied it, nice. So you could definitely use something that is close or similar to the concept of the KL divergence, right? So definitely you can find the difference between these two distributions and then basically just try to optimize that difference. Now, the algorithm that we are going to see is exactly similar to what we have just described, right? So it's a simple algorithm that, or a simple thresholding requires manual selecting of the threshold value. And if we, as you said, we just try to find the peaks using some algorithm, again, we will have to do it manually. So Otsu's method automates this selection. So what its assumptions are. So it assumes that our image contains two classes. So it assumes that we must have these two probability distributions, right? So in the case of an image, like with a white cat on a white background, we will have everything like this. So this assumption is not there. So meaning it must have a background and foreground which are different from each other. But it does not make any assumption about the size of each one of them, right? So it assumes also that grayscale histogram of our pixel intensities of our image is a bimodal, which simply means that the histogram has two peaks. These two peaks, again, is the direct response of the first assumption. So this second assumption is kind of like a reinforcement of the first assumption. So what we're trying to do is we're trying to compute the threshold that achieves the following: the smallest within class or intra-class variance and the largest between class or interclass variance. What does it mean? We're trying to group, or we're trying to say it like this. If I say that this is the split, then the variance in this part should be very small. The variance in this part should be very small, but the variance between them should be as big as possible. So let's do the following, right? Imagine this one. So this is our histogram, where the values of the pixels are very far from each other. In this case, all of this region can be useful for us, right? All of these values are good enough. But in these cases where they are closer together, let's take, for example, this. Yeah, if I'd say the threshold is here, then the standard deviation of this part on the left would be very high, right? So you have some values here, some values here. The standard deviation of this class would be like 18, right? But if I say the threshold is here, then the standard deviation of these values would be very small, like 2. and these values would be also very small too. So you see what the goal of this algorithm is to put a threshold such that when we compute the standard deviation of the two sides, it is at its lowest. Simple. Is it simple? Can somebody give me like an iterative approach to do this, right? So a very simple search algorithm.
You can try analysis.
Exactly, like we can go for like for I in, or let's say for threshold in range from 1 up to, let's say, 254. For each one of these values, what we will do, calculate standard deviation left. Let me just write. Yep. Calculate STD left plus STD right. And then we like find minimum of this one. So right, if sum is smaller than minimum, then minimum equals sum and best equals t. And that's it. So this is the simple algorithm that you guys have made. So it's definitely a long algorithm because it will be calculating standard deviations multiple times, right? But can somebody tell me how would this, let's say, yeah. So let's say we have here is our, yeah, this is our big line, right? How do you assume the sum would look like? Remember that STD left plus STD right. How would you assume that the shape of this sum would look like while we are moving the threshold?
Like a parabola.
Yeah, something like this, right? So it should look something like this. If we have these two assumptions, then the shape of this function should look something like this. Do you really need to look like pixel by pixel in this case? Or are there like easier algorithms to do this?
Ternary search.
Yeah, so we could like take a point here and then take a point in here. If there's like a decrease, we go. If there is not, we don't go. So there are definitely some better algorithms to use than direct search space. But again, it's one thing. So this is like just an optimization problem, right? So this is just like a small explanation. This is how it's being calculated. So first we calculate the mean of the pixels. We calculate the variance of those pixels. And then we calculate something called as the weight. The weight is just how many samples do you have, right? So let's say for the background, we have, let's say, 70%. And for the foreground, we have 30%. So this is what the weight is, like how many pixels are in the foreground, how many pixels are in the background. The mean, simple. So this is what you calculate after you do the thresholding. So let's say this was our distribution. Let's say we started, this is the threshold that we chose. So the mean of the background is the mean of these samples. The mean of the foreground is the mean of these samples. So calculating this is easy. Calculating the variance is also, again, very easy. We calculate the variance of this place and the variance of this place. Sorry. So the interclass or intra-class variation or within class variance is equal to the sum of the two variances multiplied by their associated weights. So again, what they say is here, as we have described earlier, we're trying to calculate the sum of the two variances, but instead of just doing the normal sum, we're doing a weighted sum based on how many pixels are in the background and how many pixels are in the foreground. So this kind of helps that function, parabolic function, be even smoother than just a normal sum. Very well. And then we have the, there you go, just different examples. And then you have the between class variance. The between class variance is calculated as follows. Mean of the background minus the mean of the foreground squared. So this is basically kind of their distance. The higher it is, the better. Or the lower it is, the better. And multiplied by each other's weights. And that's it. So this is basically overall what is happening. Now let me ask you a small question, right? If I multiply 0.5 by 0.5, how much do I get? If I multiply, is this correct? No, this is not correct. Like this, right?
No.
No.
I'm horrible with math. Huh? So it's 5 times 5, which is 25, divided by 100. Yeah, it's like this. So it's 0.25. For some reason, it looks weird. Yeah, okay. So it's like we're dividing 0.25 by 2. Okay. 0.9 multiplied by 0.1. How much is this?
0.09.
0.09. So basically, if their sum is equal to 1, then the highest value for the multiplication will be 0.5 multiplied by 0.5. So this is just to understand what this term does, right? So this term aims at getting a distribution that is kind of as equal as possible between the two of them, right? So it's trying to like give you something kind of balanced, right? Now just to see how the Otsu's method looks like. So here you can definitely see that it's doing a good job. It's doing a very, very good job, right? But it has some few issues. Some of these issues are the following, right? So you see these pixels? These are like pixels from the background, which are taken with the mask. And also you can see here, for example, in the foreground, there are some problems like in the pixels for the foreground, there are lots of holes, which there shouldn't be. Like, so this hole exists, but this like tiny hole here does not exist. So this was a problem. Sorry, this is a problem of the algorithm. Another method is band thresholding. So instead of doing something that is like, how do we say this? Instead of thresholding based on one value, now we are thresholding on two values, right? So we threshold, for example, from here to here, and we get something like this. For example, we threshold from here to here, and we get something else. So using this, we're able to have a bit more control. So basically, instead of having just one threshold, we have multiple thresholds. Now, semi-thresholding is a very similar technique, but to first type of thresholding. But in this case, instead of having one in the mask, we just keep the same original value, right? So for example, this is our mask. And here, instead of having just one white value, right, for all of them, we keep the original grayscale value. So this is just, it's not a technique, this is just a small definition, right? Now, adaptive thresholding. Remember this idea of having multiple thresholds, right? Let's try to take this idea a bit further, right? So why do we have just one threshold? So why do we have just one or two thresholds? Why not have a set of thresholds that we can define however we want? So remember one thing, like in the start, Yes. When we described this idea, we said there is like this global threshold T. Now, somebody can clearly propose something else, right? Why do we have a global threshold? Why not have a local threshold? So basically, we do something like this. So this is like something very similar to convolutions, right? We walk through the image and segment it part by part.
We
Do you
can
think
do
this
it
is a
by
good idea?
clustering.
No. We're just doing the same thing as segmentation, right? So we're doing, for example, segmentation based on Otsu's method, but we don't do it on the whole image. We do it only on a small part of the image. So for example, only here, and only here, only here, only here, only here, only here, only here, only here. So for each one of these different windows, we're gonna have a different threshold, right? So we're going to apply Otsu's method from scratch, and it will give us a different threshold for each one of these different windows. Good idea or bad idea? Of course, it does take a lot more time, but it will give us much better results. Why? Because we assume that locally, the changes between the pixels should not be too big. Like there shouldn't be something like too dangerous to work with. Let's say, for example, here, we have this problem of the small cat in here. Yeah, we have this cat that occupies only 10% of the space. Remember when we said that this case is very bad for the average threshold. So if we take the average pixel and we use that as the threshold, this case is very bad. It does not help us because the background is too big and it will not be able to do the separation correctly. But if we were working on this part of the image, right? So we were working only on small parts of the image. We're not working on something very big, you see? So in all of these cases, you will have a good distribution between both the, between both the background and the foreground, allowing you for a better thresholding, right? One would say that the global thresholding, for example, in this case, doesn't work very well because you see, it gives very bad results because it's using the same threshold for all of the image. Now with adaptive mean thresholding, what it's doing is at every step, it finds the best threshold. This allows you to get like a certain image that is much more clearer than the others, right? At every place, it still gives something clean. And to improve this further, we can use this adaptive Gaussian thresholding, which kind of cleans up the noise of this operation. So this one is a very simple algorithm. Basically, we take a kernel and we find the mean threshold, or we use the mean threshold as your friend has suggested before. How much time do we still have? 43, okay. So the assumptions of adaptive thresholding is we have smaller regions of an image are more likely to have approximately uniform illumination, right? So they all look kind of the same in terms of illumination, right? So the problem in this case is that it's illuminated differently, right? So this place is kind of darker and this place is kind of lighter. And this implies that local regions of an image will have similar lighting as opposed to the image as whole, which may have dramatically different lighting for each region. So a small question would be, what about the size of this neighborhood? So we can do something like this very small, or we can do something a bit bigger, right? It depends. Of course, the size of the neighborhood is very important in this algorithm, but in fact, empirically, there is a very broad range of neighborhood sizes that will give you very good results. So instead of trying to tune the best or find the best T, which in most cases does not even exist, tuning the best neighborhood size is a much easier job. So, so far, let's just quickly recap what we have seen. So we have seen that there are different thresholding techniques. We have seen what thresholding is. We have seen that it could be used to separate the background from the foreground. We've seen it's not an easy technique. We have seen how we can use these bimodal histograms using the Otsu's method, which is basically just finding the best threshold that computes or achieves the smallest within class variance and the largest between class variance, right? Meaning we are trying to reduce this one and we're trying to maximize this one. And how do we do that? We simply do it by a small search algorithm, right? Or we can improve that using some optimization algorithm. We have seen that there is band thresholding, which uses 2 thresholds for the whole image. We have seen something called as semi-thresholding, which does not give a 1 to all of the pixels, but instead keeps the original grayscale value. And we have seen adaptive thresholding, which uses a window to basically find the threshold at each point. And then there is this adaptive Gaussian thresholding, which basically, instead of taking the average, now it's taking like this. Let's say, for example, here it's 5, 2, 1, 1, 1, 1, 1, 1, 1, 2, 2, 2, 2, 2, 2. Right. So this is like something that could look like a Gaussian filter, right? Yeah, basically it's something like this. In the middle, it's very high. In here, it's lower. Something that we have seen already before. Yes, nice. Now let's speak about detecting edges, right? Edge detection or image gradients. We have 15 minutes. I'm sure we can finish this part, but we should definitely try. Okay, so the aim of edge detection is basically to find the edges of an image, right? So basically these things. So these are the edges of this image, for example, and they are a significant change in the intensity in a small region of the image, right? So here we can clearly see that the pixels in this area and pixel in this area are much different from each other than, let's say, the change in pixels from this area to this area, right? So this is what happens when you have a boundary or a edge. Same thing can be noticed between the pixels of this area and the pixels of this area. Because of this edge, we see that there is a huge change in the pixel intensities. So we define a local edge in an image to be a transition between 2 regions of significantly different intensities. Of course, even in this case, in here and here, there is a change in the intensities, but it's not like significantly different, right? Sorry. So edge detection is a very crucial tool, particularly in the areas of feature extraction from image for image segmentation. So let's see what an edge actually kind of looks like, right? So an edge is a place for rapid change, right, in the image intensity function. And the usage of derivative is a very good tool for the detection of these rapid changes. So let's take, for example, this case. So here we had like a stable kind of thing. So here, let's say this was this part. So here we are speaking about this part. And then we quickly went to a change of intensity. So if we draw this just like one-dimensional stuff, right? So we're working only on 1 dimension, imagine. We'll start speaking about how to see in different dimensions, but for now, we have something like this, right? So the intensities of the pixels like this are changing something like this in the same region, and then they quickly jump to something else. And of course, for example, they go to another region. Here, the intensities are in another region. So this is what's happening. If we take the derivatives of this function, it would look something like this. Of course, one person would say, how do you calculate the derivative of a non-continuous function, right? So this looks like it's a continuous function, but in reality, it's a not continuous function. We all know that. So it's just a step function, but it's like smoothed out a little bit. So here, the first derivative tells us where the edge is, right? So we can definitely see that the derivative kind of gives you 0 when there is no change, then gives you a high value when there is a certain high change, right? So derivative measures rates of change, high when there is sudden change, and where there is no change, it is 0. An edge can be detected by two types of derivatives. First is the first derivative, and of course the second derivative, which kind of look like this, right? For this one, for the first derivative, we are looking for like local maximums and local minimums. But for the second derivatives, we're looking for crossing zeros, right? Or for zeros. So in this case, for example, here is the intensity profile. Here's how they look like. We went from something dark to something light, and then went back to something dark. Here we went from something light to something dark, and then we went back. If we take the first derivative of this function, they would look like this. Right. So they give you different peaks in the place of the change. Here also they give you a different peak in the place of the change. So this is just one way of calculating the peaks. Now, if you go for the second derivative, it could be easier to calculate, or it could be easier to work with, because you're not going to be looking for like local maximum and local minimum. Again, these are, what are they called? They're not like functions. They are kind of like empirical functions, right? So they're just values, they're not continuous. But for second derivatives, it's much easier to work with, because you have just like this. This is the kind of function you are working with. So imagine our function is in reality an array of values, right? So it's not a continuous function, it's an array of values. It's not like f of x equals 5x squared. It's an array that has different values. It's easier to find out where we have a 0, or where we cross the 0, than it is to find out where we get a local minimum or local maximum, right? So because we have to define what the word local means. So this is why we use these second derivatives. They're much useful, more useful. So if you would like to calculate, of course, the first derivatives, so f prime of x equals the limit, or yeah, the limits of this when h goes to 0, right? We studied this in French, so it's a bit more difficult for me to do it for you guys. But basically what we are doing is we are calculating f at x plus h. So h is a very small value, right? So let's come here. Right. So we are working, this is x. This is f of x. Let's imagine x as a very, very small value. And what's happening is we are putting, so for example, h, for example, yeah. So this is f of x plus h, right? There it is. So we're calculating this difference compared to this difference, which is x plus h, right? Yeah, so x plus h minus x, which is just h. So this is what, in fact, we are doing, but we're doing it on a much smaller scale, right? So h is super small that you cannot see. Now, this is in the case of continuous functions, right? But the very big problem of our image is that it's a 2D, this is the first problem, and it's a discrete function. So this is why we can do something called as the finite difference approximation, which is kind of like a derivative, but in this case, h is not like super small. H is actually a value, right? So instead of h being, let's say, 0.00000000 infinitely small, h now is 1, or h is 2, Of course, the larger the h, the less accurate it will be, right? But the closer to 1 it is, the better. So this is like how we approximate the first derivative and the second derivative, of course. There are different types of finite differences, which are very commonly used. There is the forward finite difference. So basically plus h in this case. There is the backward finite difference, or the minus h. So if we are at x, we're looking at x minus h. So we're looking backwards. And of course, there is the central finite, the finite difference, which is 0.5 forward and 0.5 backwards. Of course, this will not work if h is not a, odd number. This is odd or even?
Odd. It won't work if it is odd, I believe.
Yeah, so basically we need it to be a multiplier of 2, right? This way, when we multiply it by 0.5, multiply it by 0.5 here, we still have a index which is natural index, right? So something that we can use to look for its value in the image, right? Nice. So for calculating image gradients, we use the central difference to approximate the gradients in x and the y direction. So just, I think we could stop right here, but just so we would see what things look like. So this is the function, right? This is how it looks like. And this is how we calculate its first derivative. So approximation by finite differences. So this is the first function. This is how we do it for the second derivative. So to understand, I think we should definitely stop here. Sobel filter is very important, and definitely we're going to, yes. Yeah, I think we're running out of time. For now, let's try to do a small recap of what we have seen. And we finish this part next lecture. Just so you guys would see what's going to happen. So basically, we're going to be calculating the derivative in the x, calculating the derivative in the y direction, and then basically we can combine them in this Sobel filter. It's kind of similar to a blurring multiplied by the first derivative. And yeah, this is the horizontal Sobel filter. This is the vertical Sobel filter. They give you different kind of results. So they give you like either horizontal edge detection or vertical edge detection, right? Yeah, there are different types of these types of filters. So you see, this is the Sobel filter, or the guy who created it, his name is Sobel. This is Prewitt, and this is Roberts filter, and this is Char's filter. All of them, they kind of do the same thing, but as you can see, they have different values and different intensities, which kind of lead to different, what are they called? Different results. So here, for example, this is the edge detection in the x direction, edge detection in the y direction. What we do is we combine both of them in this kind of setting using this small formula, pixel by pixel. And then we threshold it, and here is the edge detection. Now let's go through the quick reminder, or like simply speak about this. So what we have seen so far is we have seen what image segmentation is. We have seen different thresholding methods, or like we've seen segmentation through thresholding. We have seen the first one, which is global thresholding. And then we have seen that it's difficult to find the global threshold. We have seen that using the model or bimodal histogram, we can find the best value using the Odd-Sooz method. And then we have spoken about a different, after Odd-Sooz method, we have seen, band thresholding, which is just using 2 values. And then we have seen semi-thresholding, which is just a simpler or more a different version of thresholding. And then we have seen adaptive thresholding, which uses a different threshold for every single segment in the image. After that, we started speaking about edges, and we said that edges are a big change in the what they called in the intensities of the pixels. And we have seen that the first derivative can tell us where these changes are by just calculating the local minimums. And then we have seen that the second derivative is even easier because it's the locations where we have these zero crossings. We have seen that our functions or our images are not continuous functions, so we cannot calculate the derivative directly. So we can approximate these differences through different formulas. This is the best formula, and after we calculate it, we get this kind of function. So remember, our function is just an array, and whenever we have these zero crossings, we have a good index, or we have a good indicator that there was a significant change in pixel intensity. So for example, here from 7 to -7, we definitely crossed the 0, 1 time. So this means that there was a big or significant change in intensities. So for now, we stop here. And if you guys have any questions, please feel free to ask. If you don't, I think your labs should be starting soon. No questions? Thank you so much. Good luck with your labs and have a great week. See you.